That was it.
I'd like to thank the organizers for putting together such a great workshop, and it's a pleasure to be here. And the title of my talk is Efficient Zero-Knowledge Proofs, a Modular Approach. But perhaps a more accurate title would be this one. But for succinctness, I'm dropping the succinct part. So everything I said about zero-knowledge proofs applies also, almost everything I say about zero-knowledge proofs applies also to these alternative settings. And the purpose, so this talk actually serves two different purposes. The first, for those who come from the theory side, is to serve as a gentle introduction to the popular recent line of work on optimizing efficiency of proof systems for practical use. So this will be a theory-friendly introduction that focuses on high-level ideas and abstractions, but hopefully it will give a good intro to some of the more applied or technical talks, and also explain the principles and what makes the systems have incomparable features. The second purpose of this talk, for those who are actually working on building better proof systems or practical ones, is to pitch for applying this modular approach that I will explain shortly. And you know, it's already been applied to some extent, but I believe that it can be applied more broadly and more systematically. So let me start. The broad motivation is that really over 30 years late, zero-knowledge is the party that it always deserved to be. And this party is driven by a lot of interest from the outside world. For non-cryptographers are actually interested in zero-knowledge as a technology. And this interest is driven by a variety of real-world applications and scenarios that motivate also interesting theoretical questions and different optimization goals than the ones we had in mind before. So all this interest generates a lot of new ideas and exciting results we'll hear about. And this is just a list, very partial list of buzzwords of efficient zero-knowledge systems that have been implemented. And, you know, really a lot of great ideas go into these systems, but as a typical byproduct of big parties, they also leave a big mess. And from an outsider's perspective, it's sometimes difficult to understand how these schemes compare to each other in terms of ideas, in terms of features. So my goal in this talk is to partially clean up the mess and make room for a new type of mess. Don't worry. Mess always appears somehow. And the modular approach I'll be advocating in this talk, if I want to capture it by one sentence, is to maximize the separation between information theoretic parts and cryptographic parts. More concretely, I will talk about two types of compilers. One that convert an information theoretic object, that I will explain what it is, into an actual proof system you can use. Okay, cryptographic proof system you can use. And the second type of general transformation converts between different types of information theoretic objects. Okay, so this is just at a high level, these two types of general transformations or compilers I will mention in this talk. Okay, so let me be a bit more concrete about what I mean. So the ultimate goal of a proof system designer is to start with some high-level specifications. So in this talk, I'm focusing on zero-knowledge for NP relations, even though some techniques that were developed in other contexts will also be useful here. So we start with having some high-level specifications, say a Python program that implements the relation that defines the zero-knowledge problem that we want to solve. And our ultimate goal is to get something we can run, right? Either an interactive or typically non-interactive protocol that we can actually use. And typically there is one intermediate step that is being used, which is converting the high-level specification, the Python program, into some intermediate representation, a zero-knowledge representation that is tailored to the specifics of the zero-knowledge protocol that we're using. Okay, you can think of it from a complexity theory point of view just as a computational model. It's typically a concrete computational model. It can also be a uniform model like a Turing machine. But ones that are typically used are either classical models such as Boolean arithmetic circuits or RAM machines, or there are these alternative models that are driven by existing zero-knowledge systems, like rank 1 constraint systems, which are close to arithmetic circuits, TinyRAM, which is close to RAM, and these QSP, QAP, SSPs. These are models that are kind of specially tailored towards efficient zero-knowledge. The modular approach I'm advocating adds this intermediate step. So between the intermediate representation and the final protocol, we have an information theoretic proof system. I will also refer to it as a zero-knowledge PCP. And this proof system is information theoretic in the sense that its security features, both soundness and zero-knowledge, hold even against computationally unbounded adversaries. So a malicious prover can be computationally unbounded, and still soundness will hold. They're typically also unconditional, but this is not necessary. So sometimes for getting the final optimization, you want to make some conjectures, say some combinatorial conjectures about soundness of certain systems. This can be useful for getting best practical performance, but you never make cryptographic assumptions. So these proof systems are information theoretic, and they're typically unconditional. And then to move, okay, and we have actually many different kinds of such proof systems that I will explain later. But then we use a cryptographic compiler to take such a proof system and convert it into something we can use. And the reason we cannot directly use these proof systems is that they inevitably have to make some idealized assumptions, like independence between different messages, or bounded access of the verifier to the proof. And these assumptions, to be actually implemented, we need to use crypto. Okay, and these final proof systems and the crypto compilers in general needs to use cryptographic tools and assumptions. And sometimes we use idealized models to bridge some gap between our understanding of the crypto assumptions and what we believe to be true. Okay, so as I said, we have many different kinds of information theoretic proof systems and many different compilers, and we can even mix and match. So you can have one type of information theoretic proof system that is matched with several different crypto compilers, and each of these types of matchings can serve different purposes. So it's not redundant. And we also have these information theoretic compilers that move between different types of information theoretic proof systems. If you look at the classical examples, you can think of compiling a PCP into a MIP, multi-prover interactive proof, or collapsing rounds in interactive, the classical goes to CIPSA result, collapsing rounds in interactive proofs. These are examples for information theoretic compilers that don't introduce any new assumptions. And finally, we can also have information theoretic compilers from different types of information theoretic objects, like secure multi-party computation protocols in the information theoretic setting, to these kinds of proof systems. So this will be actually Muthu already talked about it during the bootcamp, and he will talk about it more during this week. So if there are any questions up to this point.
Yes. So zero-knowledge PCP on the slide is like a family of objects, or is it like?
Yeah, this is a collection. This is a broad term that describes many different types. You can also drop the zero-knowledge if you make, say, you restrict the number of queries. So I will give a very concrete idea of different types of information theoretic proof systems that I just refer to them collectively as zero-knowledge PCPs.
So these compilers that you mentioned as examples are not necessarily zero-knowledge. It's just sort of...
Yes, they're not necessarily zero-knowledge. Zero-knowledge, in this domain, there are very few results that cannot be made zero-knowledge at a low cost. On the other hand, in some cases, you only care about zero knowledge and you care less about other features, like succinctness. Okay, so why this modular approach? I guess that in general, I don't need to really work hard to convince you that the modular approach is good. It simplifies things. We can optimize each component separately. I guess that this last bullet here is specifically relevant because we have very little hope of proving negative results on the final systems. However, the information theoretic component is something we can try to analyze, to optimize, and even prove lower bounds. So far, there haven't been that many results, but there is hope to prove lower bounds. And sometimes failing to prove lower bounds gives us new ideas for upper bounds. This has happened many times and can happen here as well. So there's already the mixing and matching aspect that I mentioned. At this point, it's a bit too abstract, but we'll see reasons why different compilers achieve different things, even when applied to the same type of information theoretic proof system. There's a lot of redundancy in the current research, a lot of recycled ideas, so this modular approach can also help minimize the number of things we need to write.
So, well, it's kind of interesting that I think that
The duplication.
that historically speaking, actually it worked the other way around, right? The first
Yeah.
result would be computational, and then it's not that it would be by taking out, but then there would be an information theoretic one. So the possibility is usually by assuming a lot, and then the observation is. But you're saying.
Yeah, I think that you know, there are certain, I will refer to even, there are cases where we cannot apply this approach. So I should say that this approach is by no means universal, but I think that in most cases, including practical ones, this approach can be applied both to theory results and to more practical constructions. Yeah, and I will discuss this extensively. And in terms of efficiency, you can take, say, a GPU-based implementation of a certain information theoretic proof system, and then combine it again with different compilers. So really, even at the level of low-level implementation, you can leverage optimization ideas that apply in one context to other contexts, which right now is very hard to do without a modular approach. And I think that maybe the upshot of all this is that we have a huge design space for proof systems. And if we want to somehow navigate it or find the right combination of existing ideas that is best for our goals, then I think that the modular approach is the best way to go. Okay, so now, yes.
With respect to the generality, would this apply to proofs of knowledge as compared to proofs of memory?
Yes, so I will not explicitly address proofs of knowledge, but everything I say applies also. So proofs of knowledge can also be defined at the information theoretic level and can be inherited by, so the cryptographic compiler can respect them or cannot respect them. Sometimes it's a matter of which assumptions we make. So yeah, so proofs of knowledge is an orthogonal aspect. It's very useful. You can say, I can broadly say that almost everything I say here in this talk has a proof of knowledge feature for free. Almost for free. Okay, so let me now give you some idea of the many different goals we can have when designing proof systems. I'm assuming here zero knowledge, but you can also consider the non-zero knowledge variants. In some cases, they're also non-trivial. And without specifying really what you want, you can't optimize, right? So sometimes there are inherent trade-offs between different features, and really, these are some qualitative features we may or may not be interested in. So, you know, we may care about the protocol being non-interactive. Nowadays, people typically expect protocols to be non-interactive, but there are also some advantages, both from a theoretical and from a practical point of view, to interactive protocols. So if you don't need it to be non-interactive, maybe an interactive solution will work better. Succinctness, right? So this is succinctness in terms of how many bits are being communicated. There are other notions of succinctness. Do we really need the proofs to be short, or maybe we have a super fast communication network and we don't really care? How about the work of the verifier? Do we really need the verifier to run, say, in quasi-linear time in the input length, or maybe we're okay with the verifier working as hard as the prover? Right? Depends on really what we're proving, how powerful is the verifier, and so on. Do we want verification to be public? Again, a typical desired feature, or are we okay with a designated verifier, or maybe pre-processing between a designated prover and designated verifier? Is the input public? Maybe it's committed, encrypted, distributed. P versus NP. Are we allowing a trusted setup?
What do you mean by zero knowledge? Sorry.
So this is mainly relevant to the non-zero knowledge, but if you'll hear later in the talk, if the input is encrypted or distributed, then it's meaningful. But also, yeah. But, also you can think of an expensive computation that, like in precise zero knowledge, right? So, yeah. But again, you can remove zero knowledge here. The first question should be zero knowledge, question mark. Okay, are we allowing a trusted setup? There are different kinds of trusted setup. Do we want to use symmetric crypto only, or are we fine with using public key crypto? Do we want to be post-quantum? This is very relevant to recent news about quantum supremacy. Yes?
Among all these issues, which issues are ability to do, if you say yes or no, it dichotomize, you are not able to do without resource, I mean, this number of bits on this number.
Yeah, so let me give you an example. So let's look at the last bullet, post-quantum. So right now, if you don't care about being post-quantum, systems that are being deployed have roughly 1,000 bits of proof, but they're not post-quantum. If you want to be post-quantum, this number grows by a pretty big factor. Okay, so the level of succinctness we can currently achieve using techniques that are not post-quantum secure is much better than using other techniques. And you can have similar examples for other questions. Okay, so beyond these qualitative features, there are also these quantitative features, right? Exactly how much communication, right? I mentioned this 1,000 bits, the world record in succinctness, where you can care about asymptotics, right? Polylog versus square root. What about prover complexity? What about verifier complexity, right? So these are like quantitative optimization goals that you can consider either at the asymptotic level or at the concrete level. So I should say that right now, again, there is a lot of effort both in implementing and even selling zero-knowledge solutions. There's an effort of standardization. We have a representative of NIST here, at least one, right? So maybe yes, two. Okay.
We're not representing the standardization process.
Yeah, but you're part of it. Of course, some people here in the audience are involved in the standardization process, present company included. And much of this workshop is really about these issues, these optimization questions. Okay, but I want to give you, so basically one could naively think that maybe, you know, after all this effort, we will come up, we'll figure out how to do zero knowledge optimally. And this will put an end to all this zoo. Okay, so obviously this is not possible, right? As I said, there are different trade-offs. We cannot have one system that beats all others in all aspects. But I want to give you a sense of how far this is from being true by giving a somewhat counterintuitive example of how even if we focus on just one aspect, let's say that we only care about verifier complexity, there are still very different notions of verifier complexity we can care about. So this is just, again, in the context of motivating the different approaches to solve these problems, the zero knowledge or succinct proof systems. So let's consider two systems that are identical, except for one difference. In the first system, the verifier performs a single hash function, like a very cheap symmetric crypto operation. And in the second system, the verifier performs a decryption of some public key encryption scheme. Okay, so typically we think of the first verifier as being faster by several orders of magnitude, right? So any implementation of the second will be slower in practice by several orders of magnitude than the first. However, and this is something we observed in a joint work with Bonnet, Sahai, and Wu, that for specific application of succinct or efficiently verifiable proof systems, what really matters is not how we typically measure efficiency, but what really matters is the branching program size, right? The branching program is a kind of a low-level complexity model, and the specific application is general purpose obfuscation. So if I want to obfuscate a complex program, I can use fully homomorphic encryption or things that by now are quite practical. And then obfuscate using ideal obfuscation. There's still an issue of instantiating this under standard assumptions, but if you make a heuristic leap of faith and you assume that you have an ideal obfuscation, we just need to obfuscate a verifier of a proof system. Right, and then everything else is done outside the obfuscation. Then we make a single call to this obfuscated verifier. Essentially, we need to do something that's slightly more complicated, but the complexity will be essentially dominated by verification. And then it turns out that if you use lattice-based encryption schemes such as regevs, then decryption is much more branching program friendly, has much smaller branching programs than this, SHA-256. So, and this, I think, is a pretty promising avenue for general purpose obfuscation. So if we have better obfuscation methods, we might be able to obfuscate this branching program friendly obfuscation complete candidate. And this crucially relies on minimizing branching program complexity of a verifier in a proof system, which is not a solved problem. We had some suggestion, and there might be better suggestions. And this also motivated us to design lattice-based designated verifier snarks that are motivated independently by post-quantum security. Yes?
So when you say it's not a solved problem, you mean it's not optimal?
Yeah, it's not optimal. It's just some proposal, and there are many degrees of freedom in general in all these problems. Okay, and you can consider other optimization goals that will totally change what you think about efficiency. Right? If you want to distribute the role of the prover, you have a different notion of efficiency and so on. Okay, so now let's go back. This was a very broad overview. Let me now try to give you a first type of information theoretic proof system by looking at the first results that establish the feasibility of zero-knowledge proofs. Okay, so we know that bit commitment can be used to get zero-knowledge proofs for all of NP, so one-way functions are sufficient. We also know that, right, so this combining two results, we also know that one-way functions are in some sense necessary for general purpose zero-knowledge. So from the 80s point of view, it seems like, case closed, time to move on. But of course, one of the reasons we're here today is that there is a lot more to want that is not given by these feasibility results. One aspect is efficiency. So let's look at the original proof of this GMW theorem. This is, for those who attended the bootcamp, this is just repeating kind of a fast version of what Muthu presented. I assume that most people here are already familiar with this zero-knowledge proof for three-colorability. So for simplicity of presentation, I will assume here that we have an ideal commitment primitive. It's like locking a number or a bit string in a box. But in practice, we implement it by an actual cryptographic commitment scheme. Okay, so the prover wants to prove that the given graph, this is the statement, X is the statement, is the graph. The prover knows the coloring of the graph, and the prover wants to convince the verifier that the graph is indeed three-colorable. Okay, so this is the three coloring. Every edge connects different colors. So the zero-knowledge proof works in the following way. First, the prover picks one of the 6 possible permutations of the colors at random and just recolors the graph according to this permutation. Okay, this is the recolored graph. Now the prover uses a separate commitment, sends a separate commitment to the verifier for each node containing the color of this node. The verifier challenges the prover to open a random pair of commitments that are connected by an edge. The prover has to comply to open these commitments, otherwise the verifier rejects. And the verifier checks that the two opened values are indeed different, have a different color. Okay, so this only guarantees that the prover, that the bad prover is caught with 1 over the number of edges probability, because there might be only one edge that violates the coloring requirement. So it has poor soundness, but we can amplify it by repeating order of E many times to get constant soundness and further amplify beyond that. Okay, so what is the problem with this proof? It's beautiful, it shows us what we wanted. One issue is that proving the security when you instantiate the commitments is considerably more subtle than it seems. If you look at the textbook of Oded Goldreich, there are like 2.5 fairly technical pages that prove that this system is indeed zero knowledge in the plain model. What happens if we want to use now a different NP-complete language, like Hamiltonicity? Do we need to redo the proof from scratch? Right, so this is one problem with this approach as presented here. And of course, there is the efficiency issue, and here we have two sources of inefficiency. One is we need to reduce the problem we care about to 3 colorability. It's an NP-complete problem, but how efficient are these reductions? Typically, they're not. And the second source of inefficiency is the poor soundness that makes us repeat the proof many times. That hurts efficiency. Okay, so typically when we're not completely happy with the solution we have, abstraction comes to the rescue, right? We can take a step back and ask what is really going on here. Okay, what's happening under the hood? And the convenient abstraction here is this default notion of zero-knowledge PCP. We'll see other types later, but this will be like I would call it classical. It's not completely classical, but this is the default notion of zero-knowledge PCP, which is like a traditional PCP with the following two differences. First of all, the prover is randomized, so it maps a statement X and a witness, an NP witness W, using randomness, it maps it to a proof pi. So pi can be a proof string over any finite alphabet. Here the alphabet is 1, 2, 3, corresponding to the colors. The second difference is that, so like standard PCP, we allow the verifier to query, to randomly choose a set of symbols to query. Here, so standard PCP, if there is no efficiency requirement, it's trivial. For zero-knowledge PCP, it's not the case. So zero-knowledge PCP is non-trivial to construct, even if we don't care about the number of queries. But to capture zero knowledge, we need to require zero knowledge from the PCP. So this means that what the verifier can see by querying the symbols can be simulated. Okay, typically we will want this simulation to be efficient. Okay, so we have an object that is very simple to define. We have completeness. We have perfect zero knowledge. In all these systems, you can assume that the verifier just tosses public coins, and the zero knowledge, I will talk about it soon, but the zero knowledge can be perfect in this setting. And we have some small soundness error, epsilon, that can be amplified via repetition. Okay, so these are the basic requirements. And in this model, it's also very easy to measure efficiency. It's not controversial, at least alphabet size, it's clear what we're talking about. Query complexity and prover computation and verifier computation may depend on the computational model, but these are the efficiency measures of zero-knowledge PCPs. And I should make some historical remark, is that here we only care about zero knowledge with respect to the queries that are actually asked by an honest verifier. Historically, the notion of zero-knowledge PCP was introduced in the work of Kilian Petrak and Tardosh, And they consider the stronger notion where even if a malicious verifier can query up to T symbols, where T is typically much bigger than the number of symbols queried by the honest verifiers, we still want zero knowledge to hold. And this notion is much more difficult to construct. And in fact, a very nice open question is to construct this malicious verifier notion of zero knowledge PCP with a non-adaptive honest verifier. So in known constructions, the honest verifier needs to make 2 rounds of calls to the PCP. So first round and then a second round. You know, in a work with Mo Weiss and Guang Yang, we managed to get non-adaptive verification, but only for witness indistinguishability, which is like zero knowledge with unbounded simulation. So that's the first open question in this talk. Yep.
The hardness of the malicious setting is because T, let's say in this setting, T is larger than 2. That's what the hardness is? Or
So for 3 colorability, even with T equals, so this is hard in the sublinear regime. Yes, the order of quantifiers that you want for every T is a parameter, and you want the number of queries made by an honest prover to be polylog. This is the typical setting of parameters. For the specific case of 3 colorability, even, you know, it's not zero knowledge with respect to a malicious verifier that makes 2 queries, because it can just query non-edge and see whether the colors are different. Right, so if you look at the 3 colorability example, a malicious verifier, even who can read 2 symbols, can violate zero knowledge.
supposedly if he reads 2 symbols, they should be 2 random colors.
No. If it's a non-edge, then you can see whether it's the same color or not. Okay, so yeah, I think that several people in this room have thought about this problem, and it seems solvable, but yeah.
Could you clarify in this particular example what does it mean, the public coin setting?
In public coin, it means that the verifier's decision whether to accept or reject just depends. You can think of the verifier as essentially a non-entity. So just in each round, you have public coins that determine the set of symbols that are being read. And the final decision whether to accept or reject is a function of these public coins and the symbols being read.
But the prover has private randomness, right? When it
Yeah, but the prover here is just computing a proof string, writing it up in the sky, and going to sleep. Okay, so
So there is no proof. It's a you're saying it's more difficult. So we don't know that it's hard for 3 coloring. It's impossible to do zero knowledge with 2 queries.
No. So this is possible. I mean, even it's definitely possible to have zero knowledge against any 2 symbols. It's also a question of the alphabet size. The problem is when you want to have a bigger. Yeah, when you want to get this T parameter, when the number of queries, take T as a parameter, it's given to the prover. The proof length can depend polynomially in T, but the number of queries made by an honest prover, by an honest verifier, is say polylogarithmic in T. That's the default setting that people consider. Okay, so how do we move from this information theoretic model? So by the way, just maybe to conclude, this is an totally information theoretic proof system. There's no, it's soundness and zero knowledge hold against computationally unbounded adversaries. And in terms of complexity, it's at least as complex as standard PCPs, and even standard PCPs, complexity questions are poorly understood, right? It's a highly non-trivial, so the non-triviality of traditional PCPs is inherited by this notion, plus we have some other open questions.
Just a syntax question.
Yeah.
So is there any chance you can give us a symbol, syntax for these parameters? Like in PCP, you have randomness, query size. Here you've added a whole bunch of parameters.
No, I don't think so. I mean, for PCPs, you can also consider bigger alphabets, and I think the only new parameter, there's no new parameter, right? Just the perfect zero knowledge. I think it's the same parameters as standard PCP. For this notion, the T, okay, so what I should say is that it turns out that for the purposes of this talk, the public coin honest verifier version is good enough. So this is an intriguing question, but it's less relevant to the construction of actual proof systems because the cryptographic compilers, in a sense, force an honest behavior on the verifier. I'm not insisting, it's just a feature of constructions. So yeah, maybe there are some other examples. It can be statistical, just to remove one parameter, or you can have epsilon, yeah.
But it's not exactly honest verifier, right? I mean, you can allow the verifier to choose an edge and query it, like
It's a public coin, it's a public coin. So the queries are determined by public coins. So the verifier doesn't, so you can think of this,
Even if a malicious verifier chose an edge maliciously, right? Your problem is...
yes, if it's perfect zero knowledge, then it's kind of implied that for any possible, anything in the support of an honest verifier. However, the key point here for this is that T can be bigger than the number of queries made by an honest verifier.
I think you can even come up with an intermediate notion where there's like some sort of like efficient public test, right? That if you pass the test, then you can like the...
Yeah. So definitely. All I'm saying is that for the purpose of this talk, you can just think of the queries as being determined by public coins, and the decision being determined by the public coins, and the results, the answers to the queries. Okay, that's good enough for the purpose of this talk. Okay, so now comes the question of compiling these zero-knowledge PCPs into actual proof systems we can use. The reason we cannot use, and I will refer to it later when we talk about efficient PCPs, but for now, the reason is really the assumption of independence between, you cannot just have the prover send a zero-knowledge PCP because then the bound on the number of queries, then the verifier can observe all symbols and then zero knowledge is lost. Okay, and you can't have the verifier just ask the prover for the symbols because then soundness is lost. Okay, so we have a variety of compilers, some more explicit, some more implicit in the literature. So the GMW compiler takes such a zero-knowledge PCP together with a statistically binding commitment and gives us zero-knowledge proofs, and there are some better versions of this, PAS and WE. Goldratt-Kahan, and this is a sublinear version with Muhammad and Amit. They give us a way to use statistically binding commitment to get constant round proofs. This is arguments. This is also arguments. Perhaps more relevant to practical proof systems, you can use the random oracle. In the random oracle model, Fiat and Shamir suggested an approach to make these proof systems, to compile such PCPs into non-interactive zero knowledge in the random oracle, which is heuristically instantiated by hash functions. This is known as the Fiat-Shamir heuristic. Okay, Alex will talk about getting rid of the random oracle. It's very problematic from a theory perspective. And this works sometimes, but still is very partial in terms. So there's still a very big gap between what we can prove about instantiating random oracles and what we believe to be true, at least for natural constructions. Okay, if you want to get NIZK using standard assumptions in a simpler way, you can just replace the proof system by a different type of proof system that is much more tricky to construct. This is an abstraction of the FLS NIZK system, and you can think of it as a general compiler, crypto compiler that uses any trapdoor permutation to convert a different type of information theoretic proof system into NIZK in the CRS model. This is classically how NIZK proofs were constructed from standard assumptions, but this is less relevant to the current talk for the most part because this model is much less convenient to work with than this original TCP model. Okay, great. So we have this abstraction, and now you can ask, can we get better parameters? Then let's still stick to the three-colorability construction. There's also a more controversial aspect about three-colorability example. It's beautiful, right? It's kind of a theory of NP-completeness meets zero-knowledge proofs. It looks like a coincidence that we have an NP-complete problem that enjoys this structure that helps zero-knowledge. So maybe finding other ways to build these ZK PCPs will give us a better idea of why they exist, right? Make it look less like magic or coincidence. Okay, so the first approach that I will just mention briefly, in part because Muthu talked about it and will talk about it, is this approach of compiling. This is an information theoretic compiler. It doesn't involve any cryptographic assumptions. And it takes protocols for secure multi-party computation, even in very benign settings that assume an honest majority or semi-honest parties, and compile them into zero-knowledge PCP. Okay, so you can take this general compiler and build zero-knowledge PCPs, and you can get actually, so initially it was motivated mainly for getting a conceptually simple or different approach for building zero-knowledge proofs. But later it turned out that it even has attractive concrete efficiency features. So from a simplicity point of view, you can take some very simple secure multi-party protocols that are information theoretic. They can assume an honest majority or an ideal oblivious transfer. So these are like very simple protocols, and use them to build zero-knowledge PCPs and then zero-knowledge proofs using crypto compilers. Recently, there's been a line of work on leveraging the simplicity of these proof systems to build, this approach of building zero-knowledge from MPC to get practical zero-knowledge proofs. They're dominated by other approaches for large statements or complex statements, but for simple ones, because they're so simple, they still can have some concrete efficiency advantages. And in fact, one of the post-quantum signatures proposals is actually based on optimizing this MPC-based approach. And I should say that this is a joint work with Kushilevich, Ostrovsky, and Sahai, this idea of generally converting from MPC to zero-knowledge. From an asymptotic perspective, we can use MPC protocols that are secure against malicious parties and are based on algebraic geometric codes. We can just have a plug-and-play use of results from the MPC literature to get something that we still don't quite have by other means, which is zero-knowledge proofs for general circuits, where the communication complexity is just a constant multiple of the circuit size, and the soundness error is negligible. So this is still, as far as I know, the only approach. Of course, you can do it from scratch without the MPC, but the techniques that are quite simple, that are based on AG codes. So the constructions are not simple, but given an abstraction of these codes, the construction is quite simple. We still don't know how to get this efficiency feature by other means. We have some related results in the PCP literature. Ron has some recent paper, but not quite this one, I believe. Okay, so one downside of MPC techniques is that we have in information theoretic MPC, unless you want to use fully homomorphic encryption or homomorphic secret sharing, which are other approaches, usually information theoretic MPC hits a circuit size barrier. So we don't have good techniques for reducing the communication complexity of information theoretic MPC protocols below the circuit size. So this is true, and this is a limitation on the power of this technique. However, there are some cases in which we can do better. One case is when you talk about special purpose problems that have structure, like problems with linear algebra or computations involving complex big non-abelian groups. So for these type of problems and many others, people in the MPC community have worked on finding ideas or some randomization techniques that allow us to build MPC protocols that use much fewer bits of communication than the size of a circuit that is used to implement these computations. So for these, I don't think this has been exploited yet, but I believe that there is a potential to make, again, it's a plug and play use. You can later optimize or understand how these things work and design them maybe in a better way. But you can just use big bodies of work in the MPC literature to get directly results for zero knowledge. Okay, and finally, Muthu will talk about going somewhat sublinear for general circuits. So it turns out that even if the total communication complexity is comparable to the circuit size, you can distribute it between many parties and then can get overall quadratic savings over the circuit size, and this is something that Motoo will talk about. Okay, so in the rest of the talk, so do I have 20 minutes or? Okay, so in the rest of the talk, I will now describe approaches for zero-knowledge proofs or succinct proofs that are fully sublinear. So think here as the communication as being polylog in theory terms. Okay, so in traditional PCPs, we typically want the query complexity to be constant and the alphabet size to be constant, typically binary. Okay, so this is like the dream object for a lazy reviewer, right? The verifier can just read a small number of bits from the proof and decide whether to accept or reject. We have this beautiful PCP theorem that says that every NP statement admits such a very efficient zero-knowledge proof. As I mentioned, you can even convert, in this regime of small query complexity, you can even convert these PCPs into zero-knowledge PCPs. Again, with respect to an honest verifier, this is much easier. And as I said before, if you try to directly convert these PCPs into systems you can use, you run into the independence problem, right? So if the verifier sends the places that he wants to read, then soundness is violated, okay, even without considering zero knowledge. Okay, so the first crypto compiler that applies to this setting is the one of Kilian and Micali, which uses a Merkle tree construction to implement a primitive that allows you to commit to a long string, namely the PCP proof, and then allows the verifier to ask the prover to open a small subset of bits. Think of it in theory terms as polylogarithmically many bits, with a small amount of communication. So this is achieved using a Merkle tree. The prover just computes this tree of hashes, and the commitment is the root of this tree. And when the verifier wants to open a leaf, say the fourth bit of the proof, the prover just needs to give the hash values along the path, along with their siblings, and this allows the verifier to check that binding holds. Okay, so this is a traditional approach that leads us to asymptotically attractive statements about zero knowledge if we also combine them with state-of-the-art PCP constructions. Okay, so we can get polylog prover overhead and polylog communication complexity. So this is very good from an asymptotic point of view. However, if you look at it more closely, you notice that even from a theory perspective, there are some issues, certainly from a practical perspective. Okay, so first we have this very redundant process of taking a witness. This is what the prover does, right? The prover takes the witness, applies this PCP encoding that in theory has polylog computational overhead, but in practice it's still very bad, despite a lot of optimization efforts. And then after he did this redundant encoding, it shrinks it back, right? So it seems like there should be some shortcut. Why? It's all in the prover's head, right? The verifier doesn't care about how this process was done, but it seems a bit redundant. Right, and again, the first part is really computationally heavy. The second part of hashing is relatively cheap. There's also an issue with the level of succinctness. So if you look at this approach and you want a reasonable level of soundness, you have two sources of overhead. One is the length of a path on the hash tree, which is logarithmic, roughly logarithmic in the computation time. And the second is the need for soundness amplification. So no matter what you do, if you make a very small number of queries, the prover can just guess them and violate soundness. Okay, so you need a substantial number of queries to get a good level of soundness. So again, it's all absorbed by the polylog factors, but you can define a clean enough framework that allows you to capture these sources of inefficiency.
What?
Okay, yeah.
You can have a small number of queries in big alphabet, right?
It doesn't help you. The prover can still get, so even if you have bigger alphabet, the prover can still, so you get to 1 over poly. So let's say you make 2 queries, still 1 over proof, choose 2. Okay. Yeah, so it helps to some extent, but still you need a substantial number of queries. And we have, so this is the classical classical crypto compiler that applies to PCPs, and we have a very recent one by Lewin Malavolta and by Bonnet, Bunz, and Fish that use a pretty heavy public key machinery to have a more succinct version of a commitment with selective decommitment. So it allows you to have a short commitment and then open a subset of the bits in a more succinct way. So this helps us, at least in theory, with succinctness, but it makes the computational overhead even worse.
Replacement to what? To the Merkle tree?
The crypto compiler, yes. So you replace the symmetric crypto that is used in the Merkle tree by some more powerful crypto, and you get shorter proof systems or argument systems at the expense of even worse computational complexity on the prover side, much worse. Okay, so there are two orthogonal ways of relaxing the classical PCP model. The first is to add more interaction. So now instead of the verifier making queries to one proof string, we can have a sequence of challenges. So it's not important if the queries are made while the process is going on or in the end. The important point is that the prover has a proof string, now there is a random challenge, now another proof string, and so on. So this was originally considered, I think the first indication for the surprising power of this interaction was given by Kalai and Raz in their work on interactive PCP. So interactive PCP allows just one proof string that is being queried and then interaction as in interactive proofs. And this was later generalized to the IOP model, which was independently proposed by Ben-Sasson, Chiesa, and Spooner, and by Reingold, Rothblum, and Rothblum, and we'll hear about it in Nick's talk. Okay, so this IOP model allows us to do both from an asymptotic perspective and especially from a concrete efficiency perspective, it allows us to do much more than we can with classical PCPs. We can get easier, faster proof systems if we allow this interaction. Okay, and practical systems such as Stark and Aurora are based on IOPs. A second orthogonal relaxation is changing the model by allowing a richer class of queries. So instead of point queries that allow the verifier to read a small number of symbols of the proof, we now allow each query to take an arbitrary inner product. So now we view the proof as a vector over a finite field, typically a big finite field. So you can think of the target soundness error as 1 over field size. And each query by the verifier is another vector of the same length, and what the verifier gets back is the inner product of the proof and the query vector. So this is a 3-query linear PCP. Okay, so the verifier gets the answers to these inner product queries, and now together with the input, it applies some decision predicate and decides whether to accept or reject. Okay, so linear PCPs have several advantages. They're much simpler to construct. So if you want pi, let's say that the efficiency requirement, yes?
Yeah. So again, what's a linear PCP?
So a linear PCP is just like a standard PCP, except that in a single query, it doesn't just read a symbol, but it takes an inner product. You can think of it as specifying a linear combination of the entries of the proof.
That's an allowed query.
Yes, this is the query model. Okay, so it makes the model more powerful. So we can do more with the model, but then it's harder to apply a crypto compiler to this model.
How does this relate already now to quantum type of,
Not as I don't know of any relation, but it doesn't say much.
So the adversary can do that as well?
Yes, okay, so an important point that I didn't mention, also we assume there are 2 different flavors, but for the purpose of this talk, a malicious prover also is bound to writing just a different proof vector, so you cannot induce other things. So,
Why did the adversary verify? Because we're talking about zero knowledge here also.
yeah. So the adversary verifier here, it's always honest. And this is good enough for the purposes of the crypto compilers.
Okay, good.
You can also consider a malicious verifier variant, and I think this is still an open problem, but you need to define it first. Yeah. Okay, so what are the advantages? So let me be quick. So they are much, much simpler to construct as a feasibility result with a constant number of queries. So the Hadamard PCP, if you take W to be the values of the wires of an arithmetic circuit that verifies the NP relation, just take these values and attach the pairwise products of all these values. So it's quadratic in the circuit size. But this is very easy to verify with, say, 3 queries. Okay, and you can trivially make it zero knowledge. And if I had time, I could present it. It's very easy to teach. We also have construction. So this Hadamard PCP is the best we can hope for in terms of simplicity, but it has a quadratic blow-up, which was eliminated in this very influential work by Gennaro Gentry, Parno, and Rykova. So they built a linear PCP based on these other computational models that I mentioned, QSP and QAP, but you can view it as a construction of a linear PCP that has linear size in the size of the circuit and can be computed in quasi-linear time. Okay, and this is the actual linear PCP that is under the hood in, say, Zcash, or in general in most pairing-based constructions. Versions of this GDPR linear PCP. Here we don't have, here the entropies have a lot of queries, so my response to Zvika doesn't apply. We can use a constant number of queries over a big field and have soundness, which is 1 over field size. So just by increasing the field size, and this helps succinctness. So the most succinct to date, by a big margin, proof systems are based on linear PCPs. If you want to optimize for succinctness, linear PCP is a better idea than using classical PCPs or even IOPs. So using linear queries.
Do you mean just the proof size, or do you mean
Proof
the
size.
verifier?
No, just the proof size, yes. Okay, there's another feature which is reusable soundness. It's a bit technical, let me not get into it. And succinctness I already mentioned, and in fact we can compile classical PCPs. This is a joint work with several people here, Bitansky, Chiesa, Ostrovsky, and Panev. We have basically a bunch of abstractions and constructions based on linear PCP, but one of these constructions take a classical PCP and sort of packs the queries into a single linear PCP over a big enough field. So we can have a 1 query linear PCP for NP. Okay, how do we compile such a linear PCP? So it's much easier to build, it's more efficient. How do we compile it into an actual proof system? Or rather, argument system. Okay, so we have 2 generations. The first generation, which is also where the model was introduced, this is a joint work with Kushilevitz and Ostrovsky, and then there were some follow-up works. If you want to use standard assumptions, just implement a commitment primitive that allows the prover to commit to pi, right? In the same way that the Merkle tree was used to implement a commitment that supports point queries, just implement a commitment that supports linear queries. And we did something like this, and it was good in terms of the prover to verify communication, but it was bad in the sense that it involved interaction and private coins. And it was also bad in the sense that the communication from the verifier to the prover was big. Okay, so so it's, again, it's not publicly verifiable, and it's only succinct, or it's only good in one direction. The second generation that was initiated by the work of Groth, which gave the first use of pairing in this context, is to have a non-interactive, publicly verifiable system that is based. So this is a general compiler. It can apply in principle to any linear PCP that satisfies some additional requirement that I will mention. But the downside is that it requires, if you want to instantiate it without using generic models, it requires some assumptions that are not nice, that are poorly understood. It requires a long and structured common reference string as long as the circuit that verifies the computation. It's not post-quantum, it's pretty slow on the prover side, but still it's good enough to be used in many applications. And as I said, this type of construction is the one that's actually in Zcash and in other systems. And the high-level idea is to use a common reference string that has the verifier's queries encrypted. Okay, so let me describe how this works. Let's try, again, we have this 3-query linear PCP, and we want to compile it into a proof system or an argument system that works without any idealized assumptions. So a natural idea is to take the verifier's queries and let the verifier encrypt these query vectors. These are 3 query vectors that the verifier wants to learn the inner product of the proof with these query vectors. So let the verifier encrypt them using an encryption scheme that supports linear homomorphism. So given an encrypted vector, entry by entry encryption of a vector, the prover, this is public, right? So this is known to the prover. The prover can compute an encryption of any inner product of the proof with any of these vectors and send it back to the verifier who can decrypt it. This can be based on almost any public key encryption scheme that, most of them give us this additive homomorphism almost for free. Okay, so now the prover takes the proof pi, computes the encrypted answers, the verifier decrypts, applies the verification predicate, and we're done. Okay, so does this work? So again, the verifier takes the queries, encrypts them using an encryption scheme that supports linear functions. The prover sends back the encrypted answers, the verifier decrypts and verifies. Okay, first problem is, how do we know that the prover can only compute linear functions on encrypted values? Well, the modern answer to this question is just assume it away. Okay, so we call it linear-only encryption, and it's a form of targeted malleability. So it's interesting. It's a more general. It's a natural special case of something known as targeted malleability. And I think that if you compare it to alternative extractability assumptions, I think it's a bit nicer because it has some win-win flavor, and you can actually assume that standard public key encryption schemes already satisfy this linear-only property. Okay, it's win-win in the sense that if we show that the Goldwasser-Vicali system doesn't have this property, it seems like it would tell us something surprising or possibly useful about this scheme, that you can get more than we bargained for. We can compute nonlinear functions on encrypted data. This could potentially be useful. Of course, it's not as simple, but at least it looks like it. The second problem, it's a technical problem that now the prover can just apply different linear combinations to different queues whereas it's supposed to apply the same pi or even mix entries of different queues. This we solve in the BCIOP paper using an information theoretic compiler that converts this linear PCP model into something stronger called linear interactive proofs that tolerates this kind of cheating. So you can think of a linear interactive proof is like a standard interactive proof, like a 2-message standard interactive proof, where both an honest and a malicious prover is restricted to computing linear function on the verifier's message. Okay, and as I said, in BCIOP, we give this compiler that moves from the linear PCP model to this stronger model. Finally, this only works in a designated verifier setting, and the first solution is just find applications where it makes sense to work with a designated verifier, and apparently there are quite a few such applications, maybe not the blockchain-style applications, but other applications of zero knowledge. And perhaps a more clever solution given by Jens Groth and abstracted in the BCIOP paper is to use a linear PCP that has the additional feature that the verifier's decision predicate is a degree 2 polynomial in the answers. If you have this feature, then you can just use pairings to encrypt, and then the verification can be done publicly. So these cryptographic bilinear groups allow you to compute degree 2 functions. Very simplistically, they allow you to compute degree 2 functions on encrypted data and do the verification or check that the result is 0 in the clear. Okay, so there is also an alternative, very different compiler based on OLE that has attractive features on the prover side, and ask me if you're interested in it. So this is another very different compiler that gives us non-succinct zero knowledge, but one that has very attractive efficiency features in terms of computational complexity. Okay, and we can, of course, combine the two relaxations by allowing linear queries and interaction combined. And in fact, the proof system of GKR and RRR, we will hear about, we'll hear about them later in this workshop. So they can both be viewed as PCPs that allow both interaction and linear queries. In fact, you make only a single linear query, and the rest is just a small amount of interaction in terms of communication. So you have a different version called ILC. I will not get into it. And nowadays, again, another thing we will hear about in at least 3 talks is you can think of it as a specialized version of interactive linear PCP that uses structured linear queries that correspond to polynomial evaluation. So think of pi as a vector of coefficients, and the query defines an evaluation point. Okay, and this is, again, it's more limited, but we have better compilers that use polynomial commitments. We'll hear about it in subsequent talks. Okay, so let me just converge. I'm running out of time. Another notion we will hear about from Alet and Henry is something known, it's a modifier of standard linear systems, both in the interactive and non-interactive, called fully linear PCP or IOP. And in this model, you don't get free access to the input, but you have to make queries jointly to the input and the proof. And this is motivated by situations where the input is not given in the clear. It's split between different verifiers, secret shared, encrypted, committed. In these cases, you cannot, the verifier does not have access to the prover. And we also want stronger zero knowledge property that also hides the input, not only the witness. So we'll hear about these notions and applications by Henry and Alet, and also Elon will give a talk related to the goal of zero knowledge on distributed input. Not zero knowledge, but efficient proof systems on distributed inputs. Maybe a little bit about zero knowledge as well. Okay, so let me conclude. And by the way, kind of a summary of this talk, or some version of this talk, is in section 2 of the Crypto 19 paper with Bonnet et al. that Alet and Henry will talk about. So if you want a more complete set of references, just look it up. Okay, so let me conclude. So I advocated this modular approach. Yeah.
So just to make sure that, so suppose you wanted to go from linear to quadratic. So what are the things that should be true about the underlying encryption scheme that you use?
So if you want,
so suppose your queries were a quadratic function of the underlying.
Yeah.
Then what do you need from the encryption scheme that would support that?
So you would need, so the crypto compiler, it depends if you're in the non-interactive or interactive setting, but I guess that the modern response is build a commitment scheme that supports opening a quadratic function.
Such that the bad verifier cannot do
More than quadratic.
more than...
So if you allow the verifier linear quadratic queries instead of linear queries, you're making the design of the proof system easier, but then the crypto compiler becomes more challenging because you need to support these quadratic queries.
And not to support more. I think that's the problem.
You always have the balance between.
Yeah, of course. Yeah. Sorry. So I take back what I said. So it's also the prover has to. You also have soundness. Yes. So it's technically incomparable. Yeah. So if you look at classical PCPs versus linear PCPs, then linear PCPs are strictly easier because a linear query is more powerful than a point query, and the prover is more restricted than in standard PCPs. But
Quadratic, whatever form.
no, but here it's a dual view of viewing. So it depends on whether you view. Yeah. So if the queries are quadratic functions, and the prover is restricted to a linear function, then you're getting an easier model to work with. But if the prover is also allowed quadratic functions, then it's incomparable. Yeah, but in any case, we'll hear about these polynomial IOP models in later talks, several talks.
Polynomial means in generalizing from linear to polynomial?
Yes. Yeah, you can think of it as a special case. I mean, there are two dual views to look at it. You can think of it as a restricted type of linear PCPs, where the proof is still an arbitrary coefficient vector, but the query corresponds to an evaluation. So like the query is, you can think of it as a vector of the form 1 alpha alpha squared and so on. This is the univariate case. Okay, so we've seen these four general types of proof systems, depending on whether you make point queries or linear queries, non-interactive or interactive. You can classify most of the proof systems in the literature into these categories. Sometimes are refinements of these. Rothblum and Vadhan show that at least in some setting you can view, you can take an opposite direction and move from any black box construction of an argument system to an information theoretic proof system. But we also have examples of constructions that inherently deviate from these templates. So constructions that make a non-black box use of crypto primitives, like this bootstrapping or incrementally verifiable computation, or PCDs initiated by Valiant. If you want to compose two proof systems, maybe we'll hear about it in this workshop, to inherit their, say, the crypto level, right? So let's say inherit the efficiency of the prover in one system and the succinctness of a second system, then you want, typically you use a non-black box crypto to do it. So this does not fit into this framework. There are really many open questions, and since I'm running out of time, I should stop, but just ask me, or I will put my presentation online. This is just a bunch of open questions. So, you know, we have so many proof systems and crypto compilers and many nice questions to explore, and I'm sure we'll see a lot happening in the next few years. So thanks.